In this video, we're going to start taking a look at section 2.3, which will be kind of an extension of ideas related to the last section in 2.2, where we have obtained volumes of regions by revolving them around an axis and then integrating by thinking about washers or disks. So what we're going to see here is that while using washers and disks was sometimes a great approach to being able to find the volume from a solid that's generated by revolving around an axis, it may not always be a great way. To kind of see why this is, take a look here really quickly at this opening motivation. I'm going to be working with the curve y equals 2x squared minus x to the third and y equals 0. And that's going to give me this region that I have pictured over here at the right. Now, when I look at this picture, of course, I can imagine taking this region that's listed here and revolving it around any axis that I would be interested in. But specifically here, I'm going to try to rotate it around the y-axis. So I'm going to take that curve and spin it around. Now you'll see I've kind of generated what the figure down here might actually look like, right? That I can kind of see this blue space here and imagine that as it rotates around, I kind of create this, I don't know, maybe like the cake, or the shape of like a bundt cake or something like that. Now I'm going to go ahead here really quickly and attempt to just redraw this picture slightly. And the reason for doing this is I want to be able to try to sketch out what the cross sections are going to look like. So let's see here. If I was to go ahead and just provide a really rough sketch of the curve, let's say that's a picture of it, then I can put a duplicate on the other end. Okay, and then I can start to connect the dots like we did in the past sections, where I would go ahead and say that I'm going to sweep across like this, and then put some dots going into the background. But I could also maybe do that down here. I could connect a dot to its mirror image at this level. So again, I come out of the page, and then I imagine I'm going back into the page. And I'd also have to do it up here at these sorts of points. So I go out of the page and back into the page. And so hopefully with this sketch here, I can start to see that, oh, okay, the shape of the cross section here appears to be that washer shape we talked about in the last section. So this should be a really easy question. I just need to tackle this using washers. And I can even probably see that that this should be a dy question, because notice that my washers here are stacking from a low position on the y-axis up to a higher position. So I'm definitely moving in a dy direction. And you may recall that if I'm working in a dy direction, one of the first things that I'm going to have to do is solve our equations, or our given functions. So I'm going to solve our equations, or our functions, for x, right? I had to do this because remember that when I want to start to measure the radii of these different size circles here that help to create the washer, I'm going to need to go ahead and measure x coordinates, right? And so since my x coordinate is determined, say for this red radius, by my function, I need to go ahead and have this in an x equals form. Okay, so no big deal here. You could just imagine taking this particular function here and starting to solve, so this says x equals. You want it to be x equals a bunch of stuff without x in it. So x equals a bunch of stuff with y. Okay, so maybe you can sit here for a moment and try to think about how we would do that. Okay. Okay, this is kind of strange. How do I get this to say x equals? Sometimes people suggest that maybe we could like factor out an x squared here, right? Like that's definitely possible. But how do I get that to say it equals x? I mean, I have to be careful. What I definitely don't want to do is something like divide both sides by an x squared and then do something like add the x over, subtract the y over the y over x squared over, and like get to something like this, because notice this isn't what we were shooting for. We don't want x equals stuff with y and with x. We just want x equals. So we're going to see here that, you know, this is actually really hard. This is hard. Need help? even put a frowny face on there, right? I mean, like, this is extremely sad moment for us. Little teardrop. Because we don't know how we might actually solve this equation to say x equals. And if we can't solve to say x equals, then there's no way that we're going to be able to measure how long these radii actually are for these circles, which means I can't actually set up the washer method. And so it's at exactly this moment when I can't set up the washer method that I may begin to search for a new technique. It would be great if this new technique didn't require a dy problem where I would have to solve my equation for x. Instead, it would be really helpful if I could tackle this with a dx problem. So that way I would not have to solve my equation for x, and I could use the equation in the form that it's currently given in. This new method is what we're going to be calling the cylindrical shell method. And in the next video, we'll describe what that method is and how exactly it works.